Hi guys, here's your promised video all about spectroscopy and how we use it. Spectroscopy is really the last topic which we have to cover, and it is very straightforward once you start to understand it. Now imagine that we're going to make propene and we're going to start with long chain hydrocarbons. We're going to use a zeolite catalyst and we'll need about 450 degrees of heat in order to crack those long chain hydrocarbons. And if you want to have a look in your book, you will find that on pages 120 to 121. Now, propene can be separated out of the mixture and then reacted with steam to make propanol. Now for this you're going to need an acid catalyst, and this is going to give us a mixture of both propan-1-ol and propan-2-ol. You can have a look at page 130 to see the details on this one. So at this point we've got a mixture, and we're going to take this mixture together and oxidize it. So let's just get this right. Rewrite it again. Now, if you look at pages 152 and 153, you'll see the details of this one. But essentially, we're going to have a mixture of products. And this is where IR and mass spectroscopy will help us later on. So in this mixture we have got propanal, which if you leave it oxidizing for too long will oxidize to propanoic acid. So let's assume that we've got propanal and propanoic acid that has been formed, and propanone, which is the compound that we want. So these compounds that we've got, these three compounds, we can separate them using their boiling points, and once we have the three separate compounds, we can use IR spectroscopy to identify the functional groups. So what I'd like you to do now is to stop the video if you haven't done so already at different slides. Stop the video now and read about IR in your books. And when you're ready to go, press play again. Essentially, IR spectroscopy is about identifying functional groups. There's going to be a limited number of groups that you will have to know, and the ones that you have to know are just drawn below. We've got the carbonyl group, C double bond O. You also have to be able to spot where you have a C single bond, O, CH, NH and OH. The best way to do this is, or to understand this, is to think about your bond as being two balls attached by a spring. When the infrared radiation is shone onto the bond at the correct frequency to make that bond vibrate, some of the infrared radiation is absorbed. Some of it will go through. The amount of infrared radiation which comes through the compound is detected. Now, when that infrared radiation of the correct frequency is shone on the bond will stretch or bend. And if it is stretched, that needs a higher energy of radiation to go through than bending. Bending is easier than stretching. The parts of the IR spectrum that you are going to be interested in are the stretches. The bends come further down the spectrum in what's called the fingerprint region, and you'll see that in a minute. So if we move on, this is an IR spectrum where everything passes through the compound. You've got 100% transmittance, everything goes through the compound, and that means that there are no bonds there that you are interested in. I mentioned the fingerprint region just before. That's below 1500, and this is where the bonds are bending. There's a lot of activity down there, and you can ignore this. What you're looking for are the large absorptions above 1500. These are the bond stretches, and I've circled those in red. So moving on to propanol, we've got some CH stretches which I've circled. They're the little jaggy lines with the big red circle around them. Ignore the sp2 and the sp3 for the moment. All this is showing you is that you've got a large number of CH bonds that are in different situations. And you've also got a large peak between 1600 and 1700, which is the carbonyl group, C double bond O. Now we're going to compare this one to propanoic acid, because propanoic acid is very interesting, and this is the next slide. Straight away you can see again you've got the carbonyl group at the 1700-1600 range, and now we've got a really large broad band up around the 3000 mark, but it goes from 3600 down to what we say that was about 2300. It's a very, very broad band. It has completely eclipsed the CH stretches, and whenever you see that on a spectrum, you know that you've got an OH bond present. Now, propanone doesn't have an OH bond, and neither does propanal. And the next one we're going to look at is propanone, which is the one that we wanted to make. And here, with the propanone, you can see that we don't have that OH stretch. So once again, we can see the CH stretches. Now, in the case of propanone with the CH stretches, you've got fewer than you had with propanal. Don't worry about that for the moment. You can see that we've also got the carbonyl bond again, which has been present throughout the whole three. But essentially, this particular IR spectrum of propanone is very similar to the IR spectrum from propanal. And this is where mass spectroscopy is going to come in handy. So we've taken IR spectroscopy as far as it will help us. We've found out what functional groups we have present, but we're having slight difficulty in telling the difference between propanal and propanone. Mass spectroscopy literally just weighs the compound. Imagine that you are taking a pot of the compound, you're cutting it up into little bits. It will measure the original compound, and it will also measure the mass of the little bits, and you get a mass spectrogram. Now, both propanone and propanal weigh 58 grams, so we hope that our mass spectrogram is going to tell us that we have got a compound that weighs 58 grams and not something heavier, which would mean that we had propanoic acid. So here is our spectrum, and this is a spectrum of propanone. You can see a large peak at 58. that shows that we've got the compound that we want. We also have some fragments, and the major fragments have been marked. We've got a methyl group, CH3, at 15. Carbon's 12, hydrogen is 1, so CH3 you would expect to weigh 15. And we've also got the C double bond O CH3 coming in at 43. Now ignore the small peak at 59. This is because 1% of carbon atoms, are heavy. They're carbon 13. So this peak that you see at 59, this small peak, is called the +1 peak. 1% of the molecules that you have will be heavy, and those will show up at 59. And the next slide shows the bits that propanone and propanal can be chopped up into. There are, of course, other bits, which was why when you look at a mass spectrum you see lots of peaks. And now your final task is to go and read about mass spectroscopy, which are on pages 170 to 175.